So next section I want to talk about is weak convergence. It's a little bit longer section and it's a very important section. It lays out the foundations of how we want to prove the central limit theorem as well. And some very important theorems within this section as well. The Haley selection theorem is a very important one. Um, so let's go through that. So definition. Um, so Fn converges to if so Fn is a distribution function. Fn infinity is also the distribution function. So Fn converges to F for all continuous points of X of F infinity. Then we say Xn is a random variable of having the distribution Fn. The Xn converges weakly. We say that Xn converges weakly or converge in distribution to a limit x infinity. And we know that as Fn uh, a double arrow to F infinity. So that's definition. And the first theorem is if Xn converges to B in distribution, where B is a constant, then Xn converges to B in probability. That's easy to prove. We want to prove that because this is Xn. So we want to prove this one goes to 0, goes to 1. So this is the inverse of greater than epsilon goes to 0. So we want to prove the inverse goes to 1. And that is just a limit of xn less than equal to b plus epsilon minus probability of xn less than equal to b minus epsilon. And that is just 1 minus 0, and that's just 1. Something we have to be aware that if xn converges to x in distribution, doesn't always indicate that xn converges to x in probability. It's true for constants, but not true in general. So let's see example. So if we let x to be a density function that is symmetric at 0, and the xn be x when n is even, and xn equals to minus x, or if n is odd, then xn has the same distribution of x. However, the probability of xn minus x greater than epsilon does now go to 0. It's an alternation of 0 and 1. So this is not true in general. However, convergence in probability does indicate convergence in distribution, which what I mean is that if xn converges to x in probability, the xn converges to x in distribution. So which tells us that x convergence in probability is a stronger convergence than convergence in distribution. And converge almost surely is the strongest one. So convergence almost surely is stronger than convergence in probability and stronger than convergence in distribution. So the proof of that is kind of a play around of the set. So which set is included in which set, and then so let's go through that. So if we want to prove xn converges to x in probability in distribution, so we want to prove this one converge to the probability of x less than equal to x. To prove that, we are going to prove two things. We want to prove the lim suit of xn less than equal to x is less than equal to x plus x less than equal to x plus some epsilon, any epsilon. And also, we also need to prove that lim inf of that is greater than or equal to xn greater than or equal to x minus epsilon. And by doing so, we have this inequality, and if we let epsilon go to 0, we get the limit of xn less than equal to x is actually probability of x less than equal to x, and that's what we want to prove. And the idea is simple. So we're gonna do a conditional split out. So xn less than equal to x, we're gonna intersect with the set of xn greater than x is less than equal to epsilon, plus xn less than equal to x intersect with the set of xn minus x epsilon is greater than epsilon. And then this is smaller set than this set by rearranging. So x this x is greater than is less than equal to x plus epsilon is a larger set of this one. And same here. So we're gonna remove this term, only left with this one because this can just go to 0 because xn converges to x in probability, and that will prove this equation and in inequality. And same as the other direction. So we want to prove the xn less than equal to x. We first look at the inverse. So xn greater than x, and that is the similar ideas, and that will be less than or equal to x greater than x minus epsilon. Just play around a little bit here. So I won't go too much. This is expanded, remove the epsilon value, and taking the xm greater than x into this inequality here, and then you get this inequality here, and this is a larger set than this one. And same here. So we're going to remove the last term here and the left with this one, and this will goes to 0. And so we get that this term, we inverse that with 1 minus this term, we get is we change the sign, less than becomes less than equal, greater than equal to, and that's what we want to prove for the limit. And that's basically what we want to prove. Not much stuff, but just playing around the sets